Well, welcome. Thank you for coming. So the first thing is we have to be able to identify acids and bases when we see them, and you are going to be expected to name acids and bases as well. So we're going to go ahead and go over some of those naming things, identifying acids and bases, or whether or not something is just a salt. And then we'll also be identifying whether or not they are strong or weak acids, because you do also need to be able to identify strong or weak electrolytes, right? So, HCl. So first of all, let's talk about basic principles of naming acids. So when you're naming acids, first of all, an acid always has an H plus, right? And typically the H plus is in front. So you can typically always tell if there's an acid because of the fact that it starts with H. So, HCl, HBr, HF, HC2H3O2. Each of these are acids. And the hydrogen in front is generally considered the acidic hydrogen. That's the hydrogen that's going to be donated. If we remember the definition of an acid and a base, an acid is a proton donor, right? And a base is a proton acceptor. So, when you're naming acids, what you have to do is look at what the H plus is connected to. If an acid, if the H plus is with a single atom ion, in other words, basically just an element like chlorine or bromine fluoride. So if an H plus is with a single atom ion, the name is simply hydro and then at this point you insert the root of the single atom ion. So typically it's the first syllable. I'm not sure if I spelled that right. I'm a chemistry major, not an English major. First syllable of the ion or element. So the first syllable of chloride or chlorine is chlor, right? So the first syllable of ion followed by an IC, ic. And then you always end with the word acid. So in this case, when H is with Cl, it's going to be hydrochloric acid. Make sense? So that's our first one. Now, if it's bromine, what would the name be? What did you say?
Hydrobromic acid.
Hydrobromic acid. And fluorine would be?
Hydrofluoric acid.
Hydrofluoric acid. So those are pretty straightforward. Now, there is a little bit of an exception when it comes to S. Instead of saying hydrosulfic acid, you actually use the word, or you actually use two syllables, sulfur, or sulfur. So it's hydrosulfuric acid. So for H2S, that's one of the few exceptions. It's similar, you still get the hydro prefix, but instead of being just the first syllable, it's the first two syllables. It's sulfur, and then add the IC. Hydrosulfuric acid. Does that make sense? It's just one exception, unfortunately. Now, what if you have a polyatomic ion? Well, there's a couple of different things you have to do here. If you have to identify what the name of the polyatomic ion is. And in this case, the C2H3O2 is acetate. It's ACETATE. That's acetate, C2H3O2. Okay? So with a polyatomic ion, if your H plus is with a polyatomic ion, and that ion has a ATE ending, if the H plus is with a polyatomic ion with an ATE ending, 8, you simply, you name it, or rather the name is the first you change the ATE to IC. Name the ion, but change the 8 to IC, and add acid. So acetate becomes acetic acid. Acetate becomes acetic acid. So let's take a look at another one that would be similar. Look at H3PO4. H3PO4. It's the 5th one down. What is the oh, that's not a good example. Look at H2CO3. That's second from last. So H2CO3, that is carbonate, right? CO3. So what would the name of the acid be?
Carbonic acid.
Carbonic acid. Carbonic acid. Carbonic acid. So H2CO3 with carbonate is going to become carbonic acid. Now, let's take a look. I'm going to erase a little bit here. Let's take a look at a couple of goofy ones too. Unfortunately, there's some goofy ones with the polyatomic ions. You have H2SO4, and just like H2S was hydrosulfuric, we had that little bit of oddity to it. When you have sulfate, instead of, I know that the polyatomic ion is sulfate, and you might want to call this sulfic acid, and that would make sense. But once again, it does that little bit of a weird thing. This actually is sulfuric acid. Sulfuric acid. And unfortunately, it's a fairly common acid, even though it doesn't follow the typical naming scheme of the acid. I mean, the 8 still becomes IC, but you end up adding that UR to it. Phosphorus or phosphate does the same thing. If you have PO4, H3PO4, you might want to call this, I mean, the ion is phosphate. And you might want to call that phosphic acid, which makes sense. But it turns out that it's another exception. You have to add that OR to it, so it's phosphoric sulfuric acid. The ATE still becomes IC, but you end up adding a couple extra letters. So I do want to make you aware of those two exceptions, just so you don't get hung out to dry. Alright, so let's go through these compounds real quickly and identify them as either acids, bases, or salts, okay? So HCl, what is that?
Acid.
That's an acid, and the name is hydrochloric acid, right? And is it a strong acid or a weak acid?
Strong.
Strong. It's one of those 7 strong acids that you need to memorize. Alright, what about H2S? Is that an acid, base, or a salt?
It's an acid.
Acid.
It's a weak acid.
It's a weak acid, and
And the name is hydrosulfuric.
a hydrosulfuric acid, exactly. So H2S is a weak acid, and is hydrosulfuric acid is the name. I'm going to go ahead and erase this part here. Alright, what about H2SO4? We already identified that as,
It's a strong acid.
it is an acid,
It's strong
And-
acid.
and it is a strong acid,
And the name is
and the name is sulfuric acid,
Sulfuric.
because we had just named that.
sulfuric.
Okay. And what about CaCl2? What is that?
CaCl2 is nothing.
It's an acid, base, or a salt?
Salt.
Salt.
It's a salt.
Yeah. Acids have H pluses in front. Bases have what?
OH.
OH minus at the end. So acids have H plus in front. Bases have OH minus at the end. Now there are more complex acids and bases, but you don't have to worry about them. You're going to be pretty much limited to the more straightforward ones. Okay. What about H3PO4? Acid, base, or salt?
So is it acid? Is it strong acid? And is it hydrophosphoric acid?
Nope. So this, what would the name of this be?
Phosphoric acid.
Phosphoric acid, not hydro. It's a polyatomic ion. You only get the hydro prefix if it is a element with the H plus. So it's phosphoric acid. Is it strong or weak?
Is this strong?
It is weak.
Weak.
It is one of the weak. It is a weak acid. There are only 7 strong acids, and that's not one of them. For the record, the 7 strong acids are HCl, HBr, HI, HClO4, HClO3, HNO3, and H2SO4. These are the only strong acids. Just these 7. Anything else is going to be weak. Now, let's look at Na2SO4. What is that? An acid, base, or salt?
And then 2 in the salt.
Salt, yep. And what would the name of that be?
Sodium sulfuric. Sodium.
No transition metal, so you would just call it sodium sulfate. Okay, cool. And what about H2CO3? Acid, base, or salt?
Carbonic
Acid. And what's the name of it?
carbonic acid.
Carbonic acid. You actually went over that, so that's good. And then
Weak.
it is weak. It's not one of the 7 strong, so it's weak. I am writing like a 3rd grader, which is offensive to 3rd graders because they write better than that. All right, so now I have NH4OH. NH4OH.
Is it base?
It is a base.
And also
Now, is it a strong base or a weak base?
is it weak base?
Yeah, it's a weak base. It's a weak base, just like this is a weak acid. Now, what's the name of NH4OH?
Ammonium hydroxide.
Uh-huh. NH4 is ammonium. It's one of those polyatomic ions that you were supposed to memorize like 2 chapters ago and probably never did. Just kidding. You probably, there's a lot to memorize in chemistry, and it can be easy to forget things if you haven't seen them in a while, so I don't blame you. But, ammonium hydroxide, there we go. So now let's look at some properties of acids and bases. These are some questions that could very well show up in your test because professors like to focus on making sure the students know the basic properties of acids and bases. So let's see if you can come up with the 5 main properties of acids and bases. Can I erase this? Are you all good? Okay. Let's pull up the 5. Let's find out what are the 5 main properties of acids and bases. Okay. And so the 5 properties of acids and bases, they mirror one another. Like here's acids, here's bases. All right. What's one property of acids? What'd you say?
Acid sour.
Sour, yeah. They taste sour. What are you doing going around tasting acids? Yeah, no, acids taste sour. Lemon juice is an acid. A lot of the really, if you like sour candies and things like that, that has typically malic acid in it. There's also other acids. They taste sour and gives a lot of fruits their characteristic tart flavor. So, what about bases? How do they taste?
This is bitter and sweet.
Yeah, they're bitter. They're bitter. They're bitter and unpleasant. And honestly, they can often be also chalky. They can actually taste kind of chalky. Not that you've eaten chalk, but I'm not sure if I spelled that right. Oh, I'm going to say I did. Alright, chalky. Now, what's another property of acids?
And maybe added to the paper that the paper gets red.
Yeah.
I don't know what's that.
Acids turn litmus paper red. They'll turn litmus paper red.
Yeah.
And by turning litmus paper red, we're assuming, of course, blue litmus paper. Because if it's a red litmus paper, it's obviously not going to turn it red, it's going to stay red, right?
Yeah.
So acids will turn blue litmus paper red. If that's the case, what do bases turn red litmus paper?
Blue.
Yeah. Bases turn litmus paper blue. What's another property of acids?
Acid?
Yeah.
Acid donor?
What's right?
Donor?
Oh, well, acids are proton donors, so that's a chemical property, but that's more kind of also a definition of an acid. What are some other properties of acids?
Is the acid polar disassociated in water?
Well,
Ionized?
other things dissociate in water too.
Yeah.
We're thinking more like, okay, well, what about its feel? How does an acid feel if you get it on you? It burns, right? You ever had lemon juice on a cut or something like that? It burns. So acids will burn or sting the skin. What about bases? What did they do? How do they feel?
Bases, nutrient.
I'll give you a hint. Soap is a base.
It's slippery.
It makes it feel slippery. It's slippery. You know why it feels slippery?
Excuse me?
Because it's dissolving your skin.
Yeah, it does.
Yeah, it's dissolving your skin. That's what happens when you wash yourself with soap. Gross, huh? So, yeah, the outer layers of skin come off when you wash your hands. That's why if you wash your hands too much, I mean, you have lots of layers of skin, so you're fine, but if you wash your hands too much, you can start to get like raw hands. Or if you like have been washing dishes all day, which sometimes happens to me after I've been cooking, and hands start to feel a little tender, so to speak, because you've lost too many layers of skin. Okay, what are some other ones? There's two more. One is related to what does an acid neutralize?
Acid neutralize?
Yeah, it neutralizes bases, right?
Oh, bases.
And which means bases likewise neutralize acids. And that is related to the proton donor, proton acceptor thing. One last one to consider is, what color are acids in the presence of phenolphthalein?
Yellow, red.
Well, acids are not red. In phenolphthalein,
Oh, just bases is pink.
yes, bases are pink.
Well, acid, I don't know. Maybe
Yeah,
blue?
orange.
Maybe blue?
Actually colorless.
Huh, yeah.
So,
Yeah, I know. Colors.
so acids are colorless in the presence of phenol.
That's why I confuse number 2 and 5 together, you know.
I actually spelled that one right. Can't spell chalky right, but I can spell that. It's like one of those names of medications that nobody can spell. You know what I'm talking about? There's this funny YouTube video where this is how prescription drugs are named, and this guy is like, is like dragging his hand over the keyboard and like smacking. All right, so let's look at some Bronsted-Lowry acids and bases. Okay, let's look at some Bronsted-Lowry acids or bases. So, everybody good with the properties here? Okay. So now we're going to look at some Bronsted-Lowry acids and bases. We're going to write down this equation. We're going to identify how to find the. I will show you how to find the acids and bases in an equation. So start with H, C2H3O2 plus H2O goes to form H3O plus and C2H3O2 minus. Okay. So you guys want me to show you the easy way or the hard way? Easy way?
Are you asking?
Okay.
Or you want to tease me?
So, first of all, let me emphasize the point that the acid and base are always reactants. The acid and the base are always your reactants. The conjugate acid and the conjugate base are always products. So, if we think about that, one thing that we can do to figure out what the acid and the base are is to look at the substances that are like each other on the product side and the reactant side. Because after an acid loses a hydrogen, it becomes a conjugate base. After a base gains a hydrogen, it becomes a conjugate acid. So what you're going to do here is look for the conjugate acid-base pairs. So if I see C2H3O2, what product or what substance on the product side is most similar to HC2H3O2?
Is a
This one, right?
yes.
So which one of these has more hydrogen?
Fiber.
This one, right?
So this acid.
So this is your acid. The one with more, when you compare the product and the reactant, the one with more hydrogen is the acid. And because it's on the reactant side, it is the acid, not conjugate acid. So I will label this my acid. And this, therefore, becomes my what? Conjugate base. It's the base, but because it's on the product side, it's the conjugate base. So now I will do the same thing, but I'll look at water and H3O+. Which of these has more hydrogen?
Which one? Fiber.
It's this one, yeah. So this is your acid, but because it's a product, it is your conjugate acid, which makes this my base. Does that make sense? Doesn't that make it easier? Good deal. So let's,
I didn't know that. We can consider that in the product we have to just conjugate it.
yes, the products are always conjugates, never acids and bases. All right. Let's take a look at the next reaction. It says SO3 2 minus. I don't know what that was, right? SO3 2 minus reacts with HCl to form HSO3 minus and Cl minus. So, what would I compare this to?
2HCl3.
This gets compared to this. Which one's my acid?
This one. It is conjugated.
It's a conjugate acid because it's a product.
The other side is base.
If that's my acid, this is my base. What about the other two here? HCl and Cl.
This is acid.
Which one?
Because it has an HCl.
HCl is my acid because it has the extra H, and this is
Conjugate.
the conjugate base. Does that make sense? That's easier, right? Go ahead and do the next three, and I'll check them in just a minute, okay? Go ahead and work those out. Okay, ready to go over? Okay. So what do we get for NH3?
Base.
Is that what you got too? Base? Alright. Which would make HNO2 your acid? Good. And NH4 was your conjugate acid? Good. And NO2 was conjugate base. Very good. What about NH4?
And it was acid.
That's your acid. CO3?
Base.
Base. This is conjugate base. And this? Conjugate acid. Very good. And then the last one, SO4 2 minus.
This is SO4 is base.
The base. Very good.
And
HClO would be then your acid, right? What's HSO4?
conjugate base.
Oh, no. It's a conjugate acid.
NH4 or conjugate base.
HSO4. And what is the ClO minus then?
Base.
Conjugate base. Now, what about the challenge question here? The one you don't have written down on your paper. Okay, so now, let's take a look at some neutralization equations and pH calculations. So you've done some neutralization equations in class, right? Right or no? Have you not really done that? Huh. It's in the book, and most classes are doing it. So, tell you what, let's just go through one, and then if you want to do the other one on your own, you certainly can. But I think it is going to be important for most of you. So let's say we have H2SO4, and it reacts with aluminum hydroxide. So whenever you have an acid reacting with a base, you're going to get what two things? Salt and water. See, some people know about neutralization equations, right? So some professors at least are talking about it. But we have to figure out what precisely that salt is, and then we have to balance it. The easiest way to do this is to first look at the charges of each of the ions here. What is the charge of H?
The charge of H?
Yeah.
Here in positive 1.
Plus 1. What's the charge of sulfate, SO4?
Minus 2.
Minus 2. What's the charge of aluminum?
Positive 3.
Positive 3. And you can figure that out from your periodic table, right? If you don't have it memorized offhand, fill up your periodic table, see where it is. And what's the charge of hydroxide?
Minus 1.
Yeah, minus 1. So, you have H2SO4 and aluminum hydroxide. Now, in this case, we know it makes a salt and water. And the reason it does that is because you're going to have a double replacement reaction. Like replaces like. So essentially, the positive charges are going to switch places. Like charges don't like each other, right? Positive charge is not going to go with the other positive charge. Instead, they're going to switch places. This positive charge is going to go with the other negative charge. And this positive charge is going to go with the other negative charge over here. You can think of it as like two couples breaking apart and forming new couples, right? You have guy, girl, guy, girl. These couple breaks apart, this couple breaks apart. Well, he's not going to start suddenly dating a boy, right? He's going to date the other girl, probably. But you never know these days. But so what are the products going to be? When you put them back together, you have to put them back together according to their charges, right? So if aluminum is a +3 over here, and it's going to go together with the sulfate, which is a 2 minus, what's the formula of that compound going to be?
N2SO4 3.
Yeah, so you have to make sure that the charges are balanced. And this goes back to the writing of those ionic compounds. You could either do the crisscross, where the -2 comes down as a +2, and the 3 for the aluminum comes down and gives you 3 sulfates, or you could do the lowest common multiple method. Since aluminum is a +3 and sulfate is a 2 minus, what's the lowest common multiple of 3 and 2 to get the charges equal? Well, multiples of 3 would be 3, 6, 9, 12, right? multiples of 2 would be 2, 4, 6, 8, etc. The lowest multiple they both share is 6, right? The lowest multiple that they both have, both 3 and 2 have, is 6. So I would need 2 aluminums to get a charge of 6. And I would need 3 sulfates to get a charge of 6. Does that make sense? Cool. Now what about the other compound that's formed?
We have here salt and we need another water.
Yeah, you need water, right? And the water comes from the fact that you have the plus 1 H over here and the minus 1 OH over here, right? So that's going to give you H2O. So now we have to balance this thing. Now, I think the easiest way to balance the chemical equation is to list out the elements, usually. That's usually the easiest way to balance it. There's also a mathematical way to do it that involves solving systems of equations. But how many of you really want to solve a system of equations to balance an equation, or to balance a chemical equation? I'm seeing some shaking of heads. I agree. It takes a lot longer, and it's only good for balancing really complex equations. But most of the time what we can do is we can get away with just listing out our elements and then balancing it. So I'll list out my elements H, S, O, and Al. H, S, O, and Al. Now some professors might encourage you to keep your polyatomic ions together. Generally speaking, I think that that is not preferable, because polyatomic ions can break apart. And for most of the students I work with, they tend to get more confused by that than be helped by it. And it's really not any harder to balance it element by element. So I just balance it element by element. All right. So how many hydrogens are on this side of the equation right now? How many? 2? Well, you remember you got to keep in mind both compounds, right? 5. So you got 5 hydrogens. Very good. And how many sulfurs do you have? 1. How many oxygens? 7. And how many aluminums? 1. And on the other side, how many hydrogens do you have over here? 2. How many sulfurs? 3. How many oxygens? 13. 3 times 4 is 12 plus 1, 13. And how many aluminums? 2. Very good. So now what we want to do is we want to balance whatever is easiest to balance first. And the easiest ones to balance, the easiest elements to balance, because we're balancing it element by element. The easiest element to balance is the one that appears in the fewest substances. So you have 4 different compounds, 4 different substances here. H2SO4, aluminum hydroxide, aluminum sulfate, and water. How many substances does hydrogen appear in? What'd you say? Well, it appears in this one, and this one, right? That's 3. So in the overall equation, hydrogen appears in 3 places. You might have said that, but I'm deaf and I didn't hear you. I'm sorry. How many substances does sulfur appear in? Just 2, right? This and this. How many substances does oxygen appear in?
4.
All 4. And what about aluminum? 2. So it looks like aluminum and sulfur are going to be the easiest ones to balance. Then I can go to hydrogen, and then at the very end, if oxygen's not balanced, I'll look at balancing that one. So, if I'm going to balance these, I'll start with sulfur. I have 1 here and I have 3 here, so what do I have to do? Yeah, put a 3 in front of this, right? So I multiply this by 3. Coefficients are multipliers, so 3 times 2 is 6, plus 3 is 9 hydrogens now. 3 times 1 sulfur is 3 sulfurs, and 3 times 4 oxygens is 12, plus 3 is 15. Make sense? Cool. So now we can go to the next element that we need to balance. Aluminum. I have 2 here and 1 here, so what do I want to do? Yeah, I'll put a 2 in front of here, right? So this will be a 2 in front of aluminum hydroxide. So I have how many aluminums now? 2. And I have how many oxygens on this side? Let's go. 18, right? Yeah. You have 18 oxygens now. And I have how many hydrogens? 12. 6 here, 2 times 3, and 3 times 2, so that gives me a total of 12 hydrogen. And now I can proceed to balance hydrogen, because sulfur is now balanced and aluminum is balanced. I have 12 hydrogens here, and I have 2 here. What do I do? 6, yeah. So 6 times 2 gives me 12 hydrogens. I'm good there. And 6 times 1 gives me 6, plus 3 times 4, 12. That's going to give me a total of 18 oxygens. And oxygen balanced itself. We balance the easy ones first, the hard ones balance themselves. Now I hope I didn't waste your time by taking the time to go through that and balancing it, but I figured since this was a little bit more challenging, I'd want to kind of show you how to do it. Let's go through some pH calculations then, shall we? Alright, so the pH calculations. It says, what is the OH concentration of a solution that has an H3O plus concentration of 1.25 times 10 to the negative fifth? Well, whenever it gives you H3O plus and asks you to solve for OH minus, or vice versa, if it gives you OH minus and asks you to solve for H3O plus, you're going to have to use this equation. Kw is equal to H3O plus times the concentration of OH minus. Now the Kw at 25 degrees Celsius, which is pretty much the only temperature you're going to deal with these, is 1.0 times 10 to the negative 14. So the equation, for all practical purposes, can be essentially thought of as 1 times 10 to the negative 14 is equal to H3O plus times OH minus. So now what you're going to do here is you're going to go ahead and plug in the value of H3O plus and solve for OH minus. Now you can plug in the value of H3O plus first, or we can just solve this equation generally for OH minus. It doesn't matter. In this case, I'll just go ahead and plug in the value for H3O plus. So this will be 1.25 times 10 to the negative fifth times the OH concentration is equal to 1.0 times 10 to the negative 14. If I want to solve for the OH minus concentration, what do I need to do? Divide what?
Division. This one division.
So I divide both sides by what?
Divided by 1.10.
Yeah, 1.25. I divide it by 1.25 times 10 to the negative fifth. And I have to do it on both sides because otherwise it does not stay equal. Both sides do not stay equal if I don't divide both sides. So this cancels out with this. And I get the OH concentration is equal to this divided by this. And what is 1.0 times 10 to the negative 14th divided by 1.25 times 10 to the negative fifth? 8.0 times 10 to the negative what?
9.
10 to the negative 9. if you're dividing by a number in scientific notation, if you do not use the e function, the EE exponent function, make sure that you put this number in scientific notations in parentheses. Because if you don't put it in parentheses, it will simply divide by this, but then multiply by this, and you'll get the wrong answer. We're going to jump a little bit back and forth, but I want to go through one of the principles of gas laws real quick with you. So, is it okay if I erase this part? Okay. Now, I don't know if your professor wants you to memorize the different gas laws, but the nice thing about the combined gas law is that all the laws are contained within it. So P1 V1 over T1 is equal to P2 V2 over T2. If the temperature is constant, then you don't have to worry about temperature, and it's just P1 V1 is equal to P2 V2. If the pressure is constant, then you don't have to worry about pressure. It's just P1 P2 or V1 over T1 is equal to V2 over T2. If the volume is constant, then you don't have to worry about volume, and it's Gay-Lussac's law. It's P1 over T1 is equal to P2 over T2. So the combined gas law has all of these together. Now when solving these, I highly recommend, especially if algebra and that type of stuff is not your strong suit, I strongly recommend solving these by first cross-multiplying the equation. Okay? So list out your variables and then cross-multiply the equation. So in this case, let's take a look at number 1 from the gas law section. It says a helium balloon containing 1.5 liters at 25 degrees Celsius is released into the air. After climbing to a high altitude where the temperature is negative 15, the volume, or what is the volume of the balloon? Assuming no change in pressure. So we're assuming no change in pressure. It means the pressure is going to be constant. We're going to ignore that piece. It's just going to be V1 over T1 is equal to V2 over T2. What I first like to do is list my variables, V1, T1, V2, T2. This also allows me to compare the units to make sure that they match. Because in this, it doesn't matter what the units are. They could be liters, milliliters, etc., but they have to match. The temperature, however, does matter. In any of the gas laws problems, temperature must always be in what unit? Kelvin. So, the V1 and T1, V2, T2, it doesn't matter where you put which, but the ones that have the same number have to go together. So if I see it's 1.5 liters at 25 degrees Celsius, those must go together. I can make them V1 and T1, or I can make them V2 or T2, but I have to put them under the same number. So I'll make them V1 and T1. 1.5 liters is the initial volume, and the temperature is 25 degrees Celsius. V2 is what I'm looking for. It says, what is the volume of the balloon? And negative 15 degrees Celsius is the second temperature. Now, because I need to put it in Kelvin, I'm going to go ahead and add 273 to each of these temperatures. And that's going to give me that's 58. Alright. So now I'm going to go ahead and plug these numbers in, but before I do, I'm going to cross multiply this equation. I'm going to change this into V1 T2 is equal to V2 T1. Do you see how I did that? Okay. Now that I've cross multiplied it, I'm solving for V2, right? So if I want to get V2 by itself, how do I get this by itself? In other words, how do I get rid of this T1?
T1.
Yeah, how do I get rid of T1?
V1, T2 divided by V2.
Yeah, they're connected by multiplication, aren't they? So you can separate them using division, the opposite. So I divide both sides by T1, and that will cancel out this and give me V2 all by itself. So then this gives me V2 is equal to V1 times T1, or V1 times T2 over T1. Now I'll plug in my numbers. I can plug in my numbers now. So my initial volume, my V1, is 1.5 liters. My my final temperature, T2, is 258. My initial temperature is 298. Kelvin cancels out and I'm left with liters. Calculate that, and what is the volume?
1.30.
1.30. With the appropriate number of safe beds. Make sense? Cool. Now, if any of these numbers don't match, like for example, if like it was pressure and the units didn't match, you'd have to convert them. Alright, let's go ahead and skip ahead to problem 3 of the gas laws. Problem 3 of the gas laws. It says, a sample of oxygen has a pressure of 489 millimeters of mercury and a volume of 269 milliliters at a temperature of 29 degrees Celsius. What will the temperature of the gas sample be if the pressure is increased to 1,052 milliliters of mercury and the volume is expanded to 125 liters? Or rather, 1.25 liters. So in this case, what equation do we need to use? I'm sorry?
Is it P1 V1 equals P2 V2?
P1 V1 equals to P2 V2 would help, but this also is asking us to solve for temperature, right? So that means...
You are looking for the which law?
The Charles law.
This is the Charles.
Well, Charles' law
This is
doesn't
not,
take
it's
it
the
into...
Charles law.
Charles' law doesn't take into account the fact that the pressure is changing. And in this problem, number 3, the pressure is changing.
And how is the Boyle's law?
Boyle's law only takes into account pressure and volume, and the question's asking us for temperature. So what do we need to use?
Oh,
So we have
Lucas
to-
law?
I'm sorry?
Hayes Lucas law?
His only accounts for pressure and temperature, but the volume is changing in this one.
Are you looking for pressure? You are looking for pressure, not temperature.
Number 3? No.
Are you looking for 3?
Yeah, number 3. No, in this case, all 3 variables are changing, so we must use the combined gas law. We have to use this one. Full form. Nothing cancels out. We have to use the combined gas law. Okay? So, first things first, let's go ahead and list out our variables. P1, V1, P1, P2, V2, T2. Now, what pressure, volume, and temperature go together? So for example, if I say my P1, my initial pressure is 489 millimeters of mercury, what's my V1?
269.
What volume goes along with that pressure, according to the problem? Remember your P1s, that's like your initial set of conditions, and your P2, V2, and T2, those are your final set of conditions. What's my initial volume?
269.
I'm sorry?
269.
260, yeah, 260, whatever it is, 269 milliliters. And what's my initial temperature?
Temperature?
29 degrees Celsius. What's my final pressure? What's my final pressure?
You are looking for.
No, that's
Are
not
you
what I'm
looking for
looking
the, okay.
What's my final pressure?
The pressure is
1052.
I'm sorry?
It's, your second pressure is 1052.
Mm-hmm. My final pressure is 1,052. It says it's increased to 1,052 milliliters of mercury. So this is my final pressure. What's my final volume? 1.25 liters. My final volume is 1.25 liters. And my final temperature is in fact what we're looking for, according to this problem. So now I have all the information. When I'm looking at this, I see a couple problems. I see a couple things that I have to do before I throw this into the equation. What do I need to do?
Is it the one to liter?
Yes, I have to convert volume 1 to liters because, or I can convert this to milliliters too, right? It doesn't matter what unit, but they have to be the same. So in this case, I'll convert the milliliters to liters. There is 1,000 milliliters in 1 liter, right? So this will actually be 0.269 liters. Okay, what else do I have to do?
Kelvin.
Yes, I have to make sure my temperature's in Kelvin, always. So this is going to be plus 273, and that's going to give me, oh good heavens, 302. 302 Kelvin. Alright, now the pressure units match though, right? So they're the same, so I can just leave it as that. I don't have to convert them to ATM. But now I need to solve for T2. Once again, I strongly recommend cross-multiplying this equation to make it easier to solve. And so if I do that, I cross-multiply this, it's going to give me P1, V1, T2 equals P2, V2, T1. Now since I'm looking for T2, identify the variable you're looking for. I'm looking for T2, I want to get this by itself. If I want to get this by itself, if I want to solve for T2, what do I have to do?
P2, P2, V2, T1, divided P1, V2, V1.
Yeah, I'm going to divide both sides by P1 and V1 to get T2 by itself, P1 and V1. P2, V2, T1 divided by P1 and V1. So now that I have this equation, I can just plug in the numbers and solve for T2. So let's do that. P2 is 1,052. V2 is 1.25, and this is the advantage of listing out your variables. Makes it much easier to see here, and much less likely to make mistakes too. Then there's T times T1, which is 302 Kelvin, divided by P1, which is 489, and V1, which is 0.269 liters. Calculate that, and what do we get?
319.
What's that?
319.
Yeah, 3,019. So, and with three significant figures, it's actually 3,020 Kelvin. Huge number, 3,020 Kelvin. Now, if you get an answer in Kelvin and it asks you for the degrees Celsius, don't forget to convert this back to Celsius. If I wanted to convert this back to Celsius, what would I do? Minus 273. And if I did that, I would end up getting 2,750 degrees Celsius, I believe. So that's how you deal with that. Now, since I know we're a little bit over time, at this point, I'm happy to go over any other of the other problems. Would you like to go over a pH problem at all? Okay, so let's take a look at a couple of these. Number 2 says, what is the pH of a solution where the OH minus concentration is 2.5 times 10 to the negative 9? So, I would go ahead and start by recognizing that pH is the negative log of the H3O plus concentration. So if I want to solve for pH, I have to get H3O plus first. It gives me the OH minus concentration as 2.5 times 10 to the negative 9. So the first thing I'm going to do is use that KW formula from before to solve for H3O plus. And I'll plug in my OH minus concentration as 2.5 times 10 to the negative 9. I then divide both sides by 2.5 times 10 to the negative 9. And if I do that, my H3O plus concentration will end up being 4 times 10 to the negative 6. 4.0 times 10 to the negative 6. From there, I can go ahead and plug that into the pH equation, and pH is equal to negative log of 4.0 times 10 to the negative 6. And what will that be? What will that give me? 5.40, right? Now remember, for pH, significant figures, when you have a pH, a logarithmic value, the significant figures are the number of places past the decimal. So this is only 2 significant figures. It looks like 3. It's actually 2 because it's a logarithmic value. Since this was 2, I need 2 places past the decimal. Alright. Now what about like number 4, where you're given a pH and you have to find the concentration of H3O plus? That's when you're working backwards. That's where we have to make use of an entirely different, well, actually it's the same equation, but if you're not familiar with logarithmic algebra, you have to kind of just memorize a new equation, shall we say. Is it okay if I erase this? Okay. So, let's say well, if I wanted to solve for the H3O plus, I move the negative over to the other side, and that gives me pH is equal to the log of H3O plus. Now log is actually base 10 logarithm. What that means is that if I raise 10 to this power, it's going to be equal to what's inside here. Essentially, just like addition is the opposite of subtraction, and multiplication is the opposite of division, raising something to a power is the opposite of a logarithm. So if I want to get H3O plus by itself, I take 10 to the log base 10 of H3O plus. And what that does is it cancels out the log part and frees this to come out in front. Of course, if I do that on one side, I have to do that on the other.
Is this question 4?
This is question 4. So that gives me this equation. Like I said, if you're not familiar with log-based algebra, you can just simply memorize this equation. H3O plus concentration equals 10 to the negative pH. Okay? Now in this case, since it gives me a pH of 2.39, all I have to do to get the H3O plus concentration is take 10 to the negative 2.39. And what is 10 to the negative 2.39? If you put that in your calculator. 10 raised to the power of 2.39. Yeah, so 4.07 times 10 to the negative third? Yeah. In this case, it'd be 4.1 times 10 to the negative third. Because remember, the pH is a logarithmic value, right? Which means that the significant figures for that pH, significant figures for that logarithmic value are only the places past the decimal. So this has two significant figures, so your answer is going to have two significant figures, 4.1 times 10 to the negative third. Although, your professor is probably not going to really care about the logarithmic sig figs because they're a little bit confusing and they only apply here. He might just be like, whatever, don't worry about sig figs. Anyway, does that make sense? How to solve for it? It's not too bad as long as you know this formula. Okay, cool. Then it says, number 5, for other gas laws, says a mixture of gases of hydrogen, nitrogen, and argon has a pressure of 1515 millimeters of mercury, 1,515 millimeters of mercury. If the partial pressure of H2 is 456 millimeters of mercury, and the partial pressure of N2 is 1.01 atm, what is the partial pressure of argon? So for this particular problem, what you're going to want to do is recognize that this is an application of Dalton's law of partial pressures. So what Dalton's law of partial pressures states is that the total pressure of any system is equal to the sum of the partial pressures in that system. So, in other words, since there are 3 gases in this system, 3 gases in this mixture, the partial pressure of hydrogen plus the partial pressure of nitrogen plus the partial pressure of argon are all going to add up to the total pressure of the system. Now the total pressure in the system is 1515, 1,115 millimeters of mercury. And it says the pressure of hydrogen is 456 millimeters of mercury. And it says the pressure of nitrogen is 1.01 atm. And it wants us to solve for the partial pressure of argon. But what is the problem with our values here? They're not the same. When you're adding and subtracting, the units must be the same. I can't add 5 cats to 4 cows, right? So I have to make sure that the units are the same. So what I'm going to do is, since the other 2 are in millimeters of mercury, I'm going to take 1.01 atm and convert it to millimeters of mercury. Now how many millimeters, to do that, I'm going to start and set up a conversion factor. What unit's going to come on the bottom here? ATM, right? And what am I going to convert to? Millimeters of mercury. Now how many millimeters of mercury is equal to an ATM? I don't know if that's something you have to memorize or if your professor will give it to you, but it is 760 millimeters of mercury is equal to 1 ATM. So, if I then take the 1.01 and multiply times the 760, what do I get? Okay, 767.6, so 768 rounded to the appropriate number of significant figures. So now what I do is I take out my 1.01 ATM and substitute in its place 768 millimeters of mercury. I can now solve for the partial pressure of argon by simply subtracting 456 and 768 from both sides. Minus 456 and minus 768. So what is the partial pressure of argon then, if I do that?
Oh, 768. 747.
I'm sorry?
747.
747 is a little high. Because I have to, remember I have to subtract 456 and 768.
291.
What'd you say?
291.
291? Sounds a little bit more reasonable. 291 millimeters of mercury. There you go. Is that what you get as well?
Just a little confused to replay the number over here.
Ah, well, of course, I could add these together first. And if I did, I would get 1224. Plus 24 units of mercury plus the pressure of argon is equal to 1515 millimeters of mercury. And then I can subtract 1224 millimeters of mercury from both sides. And so, of course, if I do that, 5 minus 4 is 1, 11 minus 2 is 9, and then that plus 4 minus 2 is 2, so 291. Does that make a little more sense?
Yeah.
Okay. And there you go. So that would be your final answer. And just for giggles, I'll go over number 4 with you real quick. So you all are familiar with the fact that 1 mole of any gas at STP is 22.4 liters, right? Have you heard that? Molar volume? So in this case, if it asks for what volume of 3.25 grams of, what is the volume of 3.25 grams of nitrogen in 2, I can take my 3.25 grams of nitrogen and convert to moles. Grams of N2 to moles of N2. To get that, I'd use the molar mass. And nitrogen is 14, so 14 times 2 is 28. So it's 28.02 grams of nitrogen is equal to 1 mole of nitrogen. If this is at STP, that means 1 mole is equal to 22.4 liters. So I can then convert moles to liters.
So where did you get it? 28.02.
That's the molar mass of N2.
Oh, okay.
Because nitrogen is 14 for just 1 atom, and 2 atoms, 14 times 2 is 28. And so that's essentially all you'd have to do for one of those molar volume problems. They're not too hard, and I'm not sure if your professor would give you the volume at STP being 22.4, so that's something you may want to check with.
Yeah. Thank you. That was the same.
So do you feel more prepared?
Yeah. I need to study a little bit more, but yeah.
Now I will actually see about going ahead and completing this answer key and posting it on the website under the workshops and events section. And so if you care to do any of the remaining problems that we did not quite get to, you will at least be able to check yourself and see if you did it right.
Where's the website?
Oh, if you Google TCC SE Science, that's 3 different words. So just let me write that down. Just Google TCCSE Science. It'll pull up our website. I also sent you a link a long time ago, I think. Although I think there's a link on each of the emails I sent for the workshops, to check out the old ones. But yeah, even otherwise, just Google TCCSE Science and it'll come up. There's also tons of practice problems and video tutorials and answer keys and practice tests and all
On the
sorts of
website?
on the website, yeah. So definitely feel free to make use of those resources. All right. Thank you for coming. Have a great day.
Thank you.
Excuse me, is this it?